Section 7.4, exponential models. And it says, example 1, suppose population of the town of Pine is given by P of t is equal to 1,500 plus 125t, while the population of town of Spruce, S of t, is given by 1,500 e to the 0.1 t, and t is greater than or equal to 0, since t is time, and it's measured in years. Find the growth rates and the relative growth rates of the two towns. Okay, so the growth rate of Pine would be the derivative, so dp over dt, which is just 125, and this would be people per year, constant all the time. The growth rate of Spruce, ds over dt, okay, now that's an exponential one, so its answer would be 1,500 e to the 0.1 t times the derivative of 0.1 t, which is 0.1, which reduces down to, I could actually write it, instead of writing it as 150 e to the 0.1 t, I could recognize this as being the original function and say that it's equal to 0.1 of s of t. Now, to find relative growth rates, I have to take the derivative, and divide it by the original function. And so if I take the derivative of, let's talk about Pine, be 0.1 s of t divided by s of t, so I end up getting 0.1, which is constant for all time. So the linear population function has a constant absolute growth rate because the derivative came out constant, and the exponential population function is a constant relative growth rate. When you're talking about exponential growth functions, they fit this formula, initial amount e to the kt, where k is the rate constant. And then we also talk about doubling time. If you're trying to find out how long it takes something to double, the time would be natural log of 2 over k. That's the formula we use for doubling time. So looking at example 2, human population growth rates vary geographically and fluctuate over time. The overall growth rate for the world peaked at an annual rate of 2.1% per year in the 1960s. Assume the world population of 6 billion in 1999, and we're going to call that t equals 0, and 6.9 billion in 2009, which that would be 10. Find an exponential growth function for the world population that fits the two data points. So we're going to start with our basic function. And the initial at t equals 0, there were 6 billion, so this turns into y of t equals 6 billion e to the kt. Then we use our other year, 2009, to figure out what k is, so we're putting in 10 for t, and it gives us 6.9 equals 6e to the 10t. And I'm going to divide that by 6, so I have 6.9 over 6 equals e to the 10t. Then I need to get the exponent out of the e, so I'm going to put a natural log through the function. So I have the natural log of 6.9 over 6 equals 10t, and then I have to divide by 10. These are supposed to be k's, not, I put in 10 for t. K, sorry about that, k. So k is going to be equal to, and we're going to have to round this, 0.014 per year. So my function would be y of t is equal to 6e to the 0.014 t. That answers part A. Part B, so there's my equation. Part B wants the doubling time. So to get the doubling time, I just take the natural log of 2 and I divide it by the 0.014, and we get approximately 50 years. So that takes 50 years to double the population. Then part C, find the absolute growth rate, y prime, and graph it. Okay, so now I've got to take a derivative. So y prime at t is going to be 6e to the 0.014t times the derivative of the junk. Simplifying that down, we get 0.084e to the 0.014t. That's a t. And then I would go to my calculator and graph it, but this function at t is 0, the answer is 0.084. So when I draw this curve, I would call this 0.084 to get the curve. And then part D wants to know, how fast was the population growing in 2010? 2010 would correspond to t is 11. And how fast means you're doing the derivative. So we are just plugging 11 into y prime, putting that into the calculator, and you get approximately 0.098, and this would be billion people per year, because the derivative made it per year, which what is that? That's like 98 million people per year.